will be about transporting quantum many-body systems out of equilibrium, but I will focus on a very particular setting, and the idea is that this particular setting will allow me to present or to show you how to obtain some exact results. Okay, so let's get started slowly. So first of all, we study a transport scenario, which means that we study a situation where there is a non-trivial flow of conserved quantities. Okay, so we want to study a situation where, like, our system is, there are, let's say, in our system, some flows of conserved quantities, like, I don't know, energy flow, magnetization flow, and stuff like that. And our goal is to basically determine such flows exactly. The second important word in the title is instead out of equilibrium. So by out of equilibrium, we mean situations where we are actually far from any equilibrium situation. In particular, this means that we can't use perturbation theory, time-dependent perturbation theory, or linear response. So out of equilibrium, no perturbation theory. No linear response. Okay? But nevertheless, our goal is to study a situation where we can actually find some exact results. So to do that, we should, of course, look at some idealized setting, some idealized situation. And this idealized situation is obtained through the following three main assumptions. So the first one is that we study the problem in the thermodynamic limit. Okay, so we study the problem when the volume of the system goes to infinity, all the densities are kept fixed, but in this way we can completely forget about any boundary effect, okay? Any finite size effect. So study the problem in the thermodynamic limit, which we often denote like lim th. So this means that volume goes to infinity, densities fixed. Okay? All right. The second important assumption we make is that we focus on stationary flows, okay? So typically what will happen is that we will initialize our system in some complicated initial configuration. Then we will wait for long enough time for all the transients to settle to zero. And then we will consider the system at that stage. So we will study stationary flows. We will study the flows that remain in this stationary limit. Okay? So study stationary flows. Which means prepare the system in some initial configuration at t equals 0, and then consider t to infinity. Okay? And the third point is that we will focus on closed system. That's strange if you think about it. I mean, what is transport in a system that is closed? All right? So we will try to define this a little bit better in the following, but studying closed systems is very useful for us because first, it doesn't, so studying closed systems, we will not need to specify any ad hoc coupling between system and environment. We will not need to distinguish system from environment, and everything will be much better defined, so no ad hoc coupling. With environment. And the second point is that the dynamics will be very easy to study. It will just be some simple unitary dynamics, okay? Sorry?
Why do you term the coupling ad hoc?
Well, because normally it's just because it's very hard normally to model what is the real coupling between the system and the environment. You're just making some assumptions ad hoc in this sense. No, just okay. Note that in principle this is not really a restriction. I mean, I can always include my baths in my system and call like what I get the resulting bigger system. I will call it system. Of course, the cases I will study will be simpler than that because I will consider system and bath of the same nature. Okay, basically I will take the system and just work with that. So I will not study like different couplings and stuff like this. Okay. Okay. So first of all, are those assumptions clear? So can we move on? Good. So a good way to obtain this situation, a very simple protocol to get to that situation is the so-called bipartite quench protocol or bipartition protocol or many other names for the same thing that we will now try to explain. All right. So basically, you initialize, you take a system, and you initially consider it made of two separated parts. Okay. And you thermalize, you take these two parts in thermal equilibrium, different temperature. Okay. So this will be some temperature, at some temperature T left, this will be at some temperature T right, and in principle you can add also chemical potentials if this conserves the number of particles. Then you quench the system at T equals 0. So at T equals 0 you suddenly join together these two. Okay? And then, so this happens at T equals 0. And then you wait long enough. So you let the system evolve unitarily. And at infinite times, what you will get is something like this. So it's very hard to draw it at the blackboard. I will try to. Okay. So, well. Like the fine lines here are like a very different temperature. You see, you will get some, I don't know, homogenization of the system. And at this point, we will focus on stationary flows here. Okay? So this is a bipartite quench. Okay, so this protocol has been studied a lot in the last years, and there are even many reviews on that. I suggest two recent ones, one by Doyon and Denis Bernard, which is a JSTAT of 2016. I have no space for JSTAT, but JSTAT 2016. And then also Vasseur and Moore. Same journal, same year, same special issue. Okay. So that's a very simple protocol. For those of you who know quantum quenches, this is basically a quantum quench when you initialize your system in some state that is not homogeneous, so not invariant under space translations, because of this, right? And let's immediately try to get some intuition of what happens when I consider such a protocol. In particular, I want you to appreciate a problem. And the problem is that generic systems, after this protocol, will unfortunately not show any stationary current. At least that's what is believed. Okay? And there are a few arguments to see that. One of them regards the so-called Fourier law. Okay? So generic systems are assumed to satisfy the so-called Fourier law. So if you have a current of some conserved charge Q, this current is assumed to be proportional to minus alpha, the derivative with respect to, let's look at gradient of Q. Okay? And the first point is that if you assume the validity of such a law, then it's quite easy to convince yourself that you will not have any stationary current. Okay? And the argument goes as follows. Yeah. There is no n. So it's proportional, so equal. And this is alpha larger than 0. Okay? All right. Basically, to see, to make the argument, you combine the Fourier law with the continuity equation. Okay. So you have the continuity equation because we said that those are conserved charges, so they satisfy with respect to E. Okay? And as I think many of you know, if you combine these two equations, you get a heat equation. Okay? Okay? But okay? And our initial condition for this heat equation, that is, there is a typo? No, I think it's, yeah, I think it's fine. Good. And our initial condition is just a step. Okay? Okay. Now I'm basically trying to make the argument in 3 dimensions, so I take this as x1 and these transverse directions as x2 and x3. But yeah, I mean, everything works really the same. These transverse directions are not very important for the argument, because the point is now to note that everything is invariant under the descaling q of x and t that goes to q of x over square root of some parameter a, t over a. Okay? Both the initial condition and the equation. So you can assume a scaling form for the solution. So q will be something like f of x over square root of t, scaling form. All right, but that's the end of the argument, because then you apply again the Fourier law, okay? And when you take the derivative with respect to x of this function, it brings you down 1 over square root of t, okay? And this quantity, of course, goes to 0 in the t to infinity limit, okay? So let me write it explicitly. This is proportional. Let me write it like this. Proportional. Let's write it with 1 tilde. 1 over square root of t. It goes to 0 for t that goes to infinity. Okay? Okay. So if I assume the validity of Fourier law, I get no stationary currents. But another way to convince ourselves that this makes sense is to assume local equilibration. Okay? So if we consider a generic system, so we take a system that has only one single conserved quantity, local conserved quantity, which is the Hamiltonian, right? The Hamiltonian is always there because we are considering unitary dynamics. So if you assume local equilibration, then we have that's our state. Let's do it a bit more formally. If we take the expectation value on our time evolving state of some operator local at point x for large x and t, we expect something like this. so that we can replace our complicated time-evolving state with a stationary state that is conserving some mild dependence on x and t. Okay? And this rho x and t stationary will be just a thermal state. Okay?
So you have incorporated the time dependence in zeta then in this kind of state.
Exactly, but it's a very slow time dependence. So this one is a crazy state, is oscillating, is like it's a really the unitary evolving initial state. That's a very complicated object. Here instead I take a stationary state that is varying slowly. Okay, this is basically the local equilibration assumption you normally do when you study weakly inhomogeneous systems. Yeah. I don't know. You decide. I would still call it auto-equilibrium, yes. Because, yeah. But, yeah, I mean, it's a matter of language. You're right. Yeah. Okay, but so if I assume something like that, all right, and then let me, for the sake of my argument, also assume that H, the Hamiltonian, right, is parity invariant. So if I reflect the space, the Hamiltonian doesn't change. So I have P dagger equal H. This is parity. All right. Then it's trivial to see that the expectation value of the current of energy on this state is 0. And the reason is that if the Hamiltonian is even under parity, then its current will be odd. So we'll have simply that trace of J energy, let me call it. It's probably not a good choice to write it here because it's not very visible. Let's use the other blackboard. Okay. Sorry. But this is equal to trace P which now I use the cyclic property of the trace to bring this one on the other side, and I commute it through the state. And I also use that J, so here I use that P, J, P is equal to minus J. So this is equal to minus trace J minus beta x t, right? So it vanishes. All right? But interestingly enough, there is a special class of systems called, yeah, please. Shouldn't I get? No, because I'm not doing so. That's a good point. So basically here I'm fixing the position x. It's all fixed. It is just a mathematical trick to show that this guy is 0. So I fix x and t, and I just use, so now x and t are fixed, right? And I just apply this operator. This is just a mathematical identity. I'm not flipping the spaces. So these are just fixed parameters.
So this is the current at the point x.
Exactly. This is the current at the point x. So I can actually remove these things. That's the same, I mean, I'm just showing you that the thermal current vanishes on a thermal state. The energy current vanishes on a thermal state for any beta, right? So now you will plug it, so that's better. So let's remove, this is true for all betas, okay? So at each point, if you assume thermal equilibrium, at each point you can use this argument and show that it's zero, that the thermal current is zero. No, here I'm assuming that the system is generic enough and I have only the energy. So yes, let's assume that I'm on the lattice if you want. So here I'm taking as only conservation law, G Hamiltonian. Of course, if I have something odd, like the momentum, this will not be true anymore. But, okay. Good. So, but I was saying, but nevertheless, there is a special class of systems called integrable systems where I have a macroscopic number of local conserved charges, and I always had something odd, even in the lattice, right? So I don't need to have the momentum. And for those systems, all these arguments will not hold. In particular, so integrable systems are systems where I have many conservation laws of the form of the Hamiltonian, which are called local. And it means that they are written, so a generic conservation law is written as, let me use a continuum notation just for simplicity. Yes? Yes. No, that's another good question. So yeah, so basically, this is the main assumption of local equilibration. You say that you have a space-time dependent beta, but the same Hamiltonian, because the Hamiltonian is the same throughout the system. So it's locally a thermal state of your system. Okay? Yes, but since basically the main assumption is that everything that is out of this small patch doesn't affect this expectation value because the operator is local. So you can just replace the full Hamiltonian and nothing changes. Okay? Yeah, that's the basic idea. All right? So I'm saying that these conservation laws, let me use a continuum notation just for simplicity, are written in this way, where this density is localized in space. It acts non-trivially only around the point x. Okay? It's some operator local in space acting in x. And for those systems, of course, the second argument I gave you doesn't hold, because as Andrea was saying, you just need to have a conserved quantity which is odd under parity and everything falls. And for those systems, Fourier law does not hold. And we will see examples of that, right? Okay? But then these form a very interesting class of systems to study after this bipartite quench protocol, because they will generate actually some non-trivial stationary currents. And in particular, they will so non-trivial stationary currents. So non-equilibrium steady states. In these systems, there will be the possibility of observe non-equilibrium steady states, normally called also with the acronym NES. Okay? So that was a very long way to introduce the title of my course. And the title of my course will then be Transport in Closed Integrable Quantum Many-Body Systems. Out of equilibrium. Okay? Now all the words make sense. Please. Yeah, so you're saying you can take a particular scaling limit where to see something non-trivial. That's your point. Sure, for sure. Yeah, that's perfectly correct. I'm not saying that it doesn't make sense to study this protocol for non-integrable systems. It's just that for integrable systems, it's much simpler. You can just take t to infinity. You will remain with a stationary current in the limit. Of course, you can take some other limits where you scale the distance and time in a different way, and you will see something non-trivial. Of course, I mean, it's possible that this happens. In particular, if you expect some diffusion, of course, you should scale x like the square root of time and see some non-trivial dependence. Yeah, this you can do, but it's just yeah, sure. I don't need any scaling. I can just take t to infinity and I see a current in zero. Yeah. Sorry? Well, I mean, yes and no, because even for non-integrable systems, you will have some linear bound on the spreading of information. For example, I take a relativistic system, the maximum velocity will still be the velocity of light, even if the system is non-integrable. Or you can use the Lieb-Robinson bound in quantum spin chains, which holds regardless of integrability. So I don't know. Yeah, at the end, yes, the important information about conservation law spreads like sub-ballistically. Yes, this is true in non-integrable systems. Okay. All right. So any other questions on this general setting? No? Everything clear? Good. So let's now get a bit more formal. Okay. Let me first, before that, let me first now sketch a main idea of the content of the course. And then we get more formal. Okay, so plan. So basically, will be 3 lectures, and in these 3 lectures we will do 3 slightly different things. In the first lecture we will study exactly, like doing the exact calculation of transporting in free systems after departitioning, after bipartite quench. In the second lecture, we will basically show a method to get the result that we got in the first lecture in 5 minutes. So, generalized hydro and in the third lecture, we will consider transport in interacting integrable systems after bipartite quench. All right, that's the main plan. Okay. Filippo, how am I doing with the time? Yeah. Okay. So I have 10 minutes or something before the break. Yeah. Okay. So in these 10 minutes before the break, I will just review. I will give a little bit more formal introduction to this thing. And then in the next hour, we will study free systems. Okay. So we basically, an important thing that I didn't mention before is that integrable models are non-trivial interacting only in 1D normally. I mean, if you go in higher dimensions, basically the only integrable systems you can find are sort of free. So I will, from now on, focus only on 1D systems, because I then want to consider non-trivial interacting 1D integrable models. Okay? So we consider a 1D system of length L even with periodic boundary conditions. So an Hamiltonian of this form. Okay? And I take this Hamiltonian density acts non-trivially on sides j and j plus 1. Okay? Then we'll take H integrable which means that the commutator of H with some Q n 0 for n going from 1 to some number m proportional to L, to the volume of the system. Okay? And these laws, these charges, are written in this way. So, as the Hamiltonian, but their density acts non-trivially from site J to site J plus R. Right? So range has range R plus 1. So it acts non-trivially on a bunch of spins or sites. Okay, as you probably know, the more experts of you will clearly know, in interacting interval models, actually you need some more than that. So you have some more than that. You have also some charges that have this density here, not exactly localized, but with exponential tails. All right? These are called quasi-local charges. But yeah, we don't need much more information about that here, but you can read a very nice review by Ilievsky, Medeniak, which we have here, so you can also ask. Rosen and Zadnik. Again, 2016 JSTAT. So quasi-local charges. Okay. All right, and this relation, let's see, what's the end of my paper? Oh, yes. Okay, the relation star implies that if I take the commutator of H with a density of charge. Now, for simplicity, I just label the density here with one index j, so it has range r, but I don't care, so it will be just h of j for me from now on. This is minus I. Okay? So from the conservation of the charge, it follows that if I take the commutator of the density of the charge with the Hamiltonian, all right, when I sum over all the lattice should be 0, so it should be of this form. Should be the same operator evaluated into neighboring sites. The difference of the same operator evaluated into neighboring sites. So then when I take the sum over j of this thing, this one vanishes. All right? So this is, if you stare to it long enough, you will understand that it is nothing but a continuity equation. Okay? So this is the operatorial continuity equation in our chain. And so there is no much imagination in calling this current. So this J operator is nothing but the current related to Q. So let's put a little Q somewhere. Well, I don't know, here. Okay. And what we will study in this system is, as we said, a bipartite quench. So what this means is the following. So we take as its initial state some row node, which has the following form. Okay, where H, L, R are just sums over J, let's say, negative and positive. So I just take the Hamiltonian I wrote before. I already erased, unfortunately. So I just take the Hamiltonian and I sum it only on positive or negative sides. So JL, let me write explicitly to one of them. HL is just sum J that goes from minus L plus 1 to minus 1 of H, J, J plus 1. And H, R is just sum from J that goes to 1, L minus 1. So basically, I take my chain divided in the following way. This is 1, this is L over 2, this is L minus L over 2 plus 1, and this is minus 1. Sorry, this is 0. Okay? And here I also put some number operators. Okay? Because I assume that my system conserves the number of particles, so I put that in the thermal state. But this is unnecessary. I can even not put it. And of course, the definition of those things, it's exactly the same as the one I gave you for the Hamiltonian. Okay? Please.
So the chemical potentials are there to signify explicitly that there is particle transfer between left and right.
No, yeah, I mean, they are just, it's a possibility. You can include them if you want. I'm just saying this. So you can force to be particle transfer. In a system conserving the number of particles, it makes sense also to force some particle transfer. Right? Okay? And finally, so of course, Z is the normalization constant, so it's the trace of the operator I wrote. So NR is 1 L over 2, the same thing. Okay, and now, so this is the stage A of my bipartite quench. Stage B is I evolve with a homogeneous Hamiltonian, right? So B, consider rho of T okay, where H is equal to H left plus H right plus the connections. So you see, I need to add these missing links. So H01 plus H L over 2 minus L over 2 plus 1. So basically I'm adding these two links. 0, 1, L over 2 minus L over 2 plus 1. So in picture, you can basically picture this quench in this way. Some people like this. And here we can put different colors for the different temperatures. Okay? I will move to this blackboard. Okay, and we will study after this quench. We will study, so this is stage C, let's say, of my bipartite quench. Study expectation values of operators defined in this way. All right. So this is the main object we will study. So we will first take the expectation value of some local observable and the time evolving state, then take the thermodynamic limit, important, very important, the order of limits. First, thermodynamic limit, and second, we will take the T to infinity limit. But we will do it in the following scaling way. So we will take the position of the observable and time to infinity with fixed ratio. Note that I can set this ratio to 0, so I can study really the infinite time limit at fixed position. Okay? It's more convenient to study these more general objects, and we will see why. Okay? So this we call scaling limit. And this is the thermodynamic limit. And let me stress again, the order matters. And the order matters because if I instead take first the infinite time limit and then the thermodynamic limit, nobody tells me that this limit will be well defined. Actually, it will not be. Because due to the unitary evolution, I will get oscillations. And so if I first take the infinite time limit, I will just get something oscillating. I would need to take some time averages to find a finite result, to find a well-defined result, not finite.
So here there is a generic to study this aspect of thought. It's a generic.
What do you mean by generic? What's generic?
It's a general.
Yes, it's a general procedure, yeah.
So my question is about this role of T. Would it feel like hard to determine?
It will be extremely hard, yes. Yeah. That's the point. Yeah, it's a very hard problem. Yeah, true. And okay, now we will try to see. Yeah, because basically, in a many-body system, this is like a terrible object, right? It's crazily oscillating with many frequencies all together. It's something hard to treat. Yeah. It's a very hard thing to treat. So it's remarkable. I mean, we will, in the general interacting case, we will manage to get the result only up in this limit, not the full result at any time. This is important. Okay? And also for free systems, to get the full result at any time is remarkably hard. Okay? All right, so I think we should have a break now and continue later. All right, so let's continue. First of all, let me make a few remarks because I had questions in the interval. So first of all, somebody asked me whether these betas here are homogeneous or not. They are totally homogeneous. They are so before the quench, these two states, apart from the boundary conditions, are completely homogeneous. Okay? First point. Second point, here we will study this limit for any local observable. For any local observable. It doesn't need to be a conserved charge, current, anything. Okay? Second thing. And the third thing I want to stress again, like in the introduction I gave before, I was trying to justify that in generic systems you don't have these stationary currents. Okay? That's true. But you don't need to be completely integrable to see any current. You just need an additional conserved charge, which is basically odd under the symmetry. Okay? So that was another question. Good. Okay. Having settled this, let's continue. Okay. So another question I just got was why we consider this particular limit, why is this sensible, and stuff like that. And I think that the best way to answer this kind of question is actually to do some calculation and to get started with some, to start building some intuition. Okay, and to do that, we consider, first of all, this protocol I just described in a free system. Okay, in a very simple system, the simplest of all. Sorry. So in particular, we consider the following Hamiltonian. Okay, where these are canonical fermionic operators, which means that they satisfy the following algebra. Okay, and I impose periodic boundary conditions. All right. So this is probably the simplest possible model one can study. They are just free fermions hopping on a lattice. So I can again draw my nice circular lattice. So this term is just the hopping term. So it kills a fermion on position j plus 1 and it creates one at position j, so just hopping. This one does the inverse process. And this one instead, it basically doesn't change the fermionic number. So if there is a fermion at position j, it gives you this contribution minus h. Okay? No, I mean, I don't need to do that. I'm just saying that, yeah, any k, but this is just because this is the only one I need in the Hamiltonian. Fine, but it is, of course, it's for any k. It's periodic by boundary conditions. That's the only ones I needed for define the operator, basically. Okay. Okay, so you know what an anticommutator is, but let me just, for convenience, remind you. That's the anticommutator. Okay, good. Okay, so in the lecture notes, you will find a nice exercise regarding this Hamiltonian. And the exercise is asking you to explicitly perform the so-called Jordan-Wigner transformation and map this Hamiltonian here in a spin Hamiltonian. Okay? And please be careful about this change in the boundary conditions. So when you map into a fermionic Hamiltonian, there will be some confusion with boundary conditions. But in order to save some time here, I will not write the Jordan-Wigner transformation. Just have a look to the problem in the notes. Okay? But like for what matters for us here, I will just say that this Hamiltonian here can be mapped in a spin chain called XX spin chain. Half. Which, neglecting boundary conditions, will be of the form I'm writing it with spins. Okay. Where these are spin halves. So are basically a Pauli matrix of x, y, z, acting non-trivially at site j divided by 2. Okay? Good. So I don't know if you are familiar with this Hamiltonian. If you're not, let's quickly mention how to diagonalize it. This is very simple. This is very simple. So what you do is you basically do a Fourier transform. So can I erase this? I just wrote it, I know, but yeah, it's not very important. Yeah. All right. So first, diagonal form of H. So we define some operators. C of k, this is a k. I'm sorry for my k, but I really can't write it better than this. Okay? You define this operator, and then you show, and you will do in the exercise, that you can express your fermionic operator in the following way. So you can basically invert this transformation, and I define the following objects. First of all, Kn. Kn is 2 pi over L times n, where n is minus L over 2 plus 1, dot, 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 L over 2. And these are all integers because I took L to be odd at the beginning. Sorry, even at the beginning. Yeah, please. This one, minus L over 2 plus 1 to L over 2. Sorry? Because my chain here, I didn't specify here the length, but it's like before. So here I have only from 1 to L over 2, then 0, and then minus L over 2. So that's the number of sides of my chain. I have a finite volume, right? That's why I'm not summing. Okay, so K is that, and then I defined also summation over the set of K's. It's a shorthand notation. So if I sum f of Kn over the set of K's, it means actually that I'm summing over n that goes from minus L over 2 plus 1 to L over 2, f of 2 pi L n. There is not much space, but I think it's clear. All right, and so you can prove this. And you can also immediately verify that if I do C of L over 2 plus K using this formula, here I get e to the I Kn L C minus n plus K, which is equal to minus L plus K, because this thing is equal to 1. The exponential is equal to 1, right? Because of the quantization conditions, because of this. Okay? So if you power this L, then you erase the L here, 2 pi n, e to the I, 2 pi n is 1. Okay? Good. Another thing you should verify, but I'm not going to do it now, is that this new operator C of K again satisfy the canonical anti-commutation relations. Okay? So if you basically, let me just reuse it. So if you just here, instead of J and I, you substitute Kn and Km, it's the same. So they are again canonical fermions. So also this you should prove it. Okay? You just use the definition and the fact that Ci and Cj are canonical. Okay? Please.
In your first definition, if you Kn, right, the diagonal form, like the very top line.
Yeah?
Kn.
No, you see, here is just a definition. So K is just a free parameter here.
But then for Cj it takes particular values.
Exactly.
Okay, so to have the two, to have the inverse relation, you need your first one to have Kn as well.
Yeah, but it's true for any K, in particular also for Kn. Yeah. Right?
Just for the record, so I think in periodicity relations, this can't be right, because it's Kn is in the sum.
Kn is in the sum. Yes, sorry, it's K. What? No. What did I write here? Yeah, that's a good point.
So each term in the sum has this periodicity property.
Yeah.
But I think it's clear.
Let me see. No. Yes, each step. Yeah. Sorry. Yeah. You are definitely right. So, sorry. Yeah. No. Let's clarify this point. So, to verify the periodicity, you just should plug here minus L over 2 plus K, and then you use that each term on this sum is equal to. I mean, you can basically replace minus L over 2 plus K with L over 2 plus K because the difference will be just 1. And then the periodicity holds. So let me write the correct version. Yeah. Then you can verify that, and you can also verify that the fermions are remaining canonical. Okay? So the last thing you should verify is that if I plug that definition, in particular, this form here, in the definition of the Hamiltonian, is a very simple calculation to show that we get the following. So, again. Too small. Where we introduced okay. Okay, something to note is that these operators here, which I will denote as n hat of kn, called mode occupation operators. Okay? These operators here commute, all of them. And you can also verify that the square of one of them is equal to itself. Okay? This is just a property of the fermions. This is just showing that these modes are fermionic, so you can't occupy more than one. Okay? Good. So that's the diagonal form of H. Then we can take profit of this diagonal form to immediately write down this family of local conserved charges for our system in a very simple way. Okay, so the first observation, and you should believe me on that, is that all, at least in the case H different from 0, all the conserved charges, the local conserved charges of the system, will be expressed as linear combinations of these mode operators. Okay? So conserved charges, let me write it. Conserved charges are linear combinations of mode occupations. Operators. When H is equal to 0 instead, there is some additional stuff, But we will not consider it here. You can have a look to Fagotti JSTAT 2014, where he discusses these additional charges that are basically coming from some degeneracy in this dispersion relation. Okay, but let's forget this and move on in writing these charges. In particular, a complete set of charges for h equals 0 is written like this. For h different from 0, it's written like this. So there will be Q naught. Okay? Like this. So if now I define this as Q0, K, this as Q2n plus 1 of K, and this as Q2n plus 2 of K, I can write all the charges in short as follows. And okay. Okay, and the exercise I ask you to do again in the notes is the following. So you should prove that these charges are Qn, Qm is equal to some constant where I define the scalar product so these charges are orthogonal in the following scalar product in operator space. And moreover, they are complete in the sense complete in the sense that if I have a charge QF written in this way that is orthogonal to all of them, then QF is 0. Okay? Sure.
Could you please define the charge operator like in the space?
Sure, I was going to do that.
Okay, sure, because this is Fourier space.
Yeah. I'm sorry? What's the constant A here? I mean, you should, I didn't, it's probably written somewhere in the notes, but now I can't find it, so you should compute it, Jerome. I don't think so, but you can put n, oh, I mean, it doesn't change much, so you can put a little n here and verify that is in the, L. Yeah, yes, it will depend on L, I think. But yeah, well, I mean, I'll do the calculation and tell you the result. Now I can't find it. I mean, all right. Okay, so let's now have a look on how these charges look like in real space. Yeah. Yes. That's a good point, and the reason is that we want to write something that is written as the sum in space of some local density, and that's exactly what I'm going to show you now, that these guys are. Okay? So now, yeah, up to now you should be puzzled, as Filippo said, because I'm just writing some combinations of what already was conserved. So what is the importance of all this? Right? So the importance of all this is that now I can write these charges in real space and like have a look of their form, which will be very explicative. Okay. So basically, Q0 is the number of particles minus L over 2. Q2 and plus 1 is I square root of 2 All right, so let's have a look to these charges. Sorry? This is plus 2, yes. Correct. So we see here that we have our nice localized densities. So these operators here act non-trivially only in the interval between j and j plus n. Okay? And you can also note that these operators here are actually parity odd. So those are nice because they can sustain some currents, some energy current, for example. Okay? And to answer Jerome's question again, I think it's linear in L, yes, that constant. It's like proportional to L. Because, yeah, we can discuss it later. Okay. Right? So having the expression for the charges, right? Can you see it now? Right? Because now I can write it as sum of local densities and I'm happy. Yes?
In the case, in the upper bound for small n, it's L halves. So the range is extensive. Is it a problem or?
It is not, I can see your point. Your point is basically that if I take n large enough, how can I consider these charges to be local, right? That's your point. And it's correct. But basically, the idea is that in the thermodynamic limit, only the most local ones will count. Okay, so those that are getting like to the edge of at the edge of the chain, actually not really. I mean, the worst case scenario is when n is close to L over 2, because then I will basically connect the two halves of the chain. So this one will become the most non-local object of all, right? So yeah, the idea is that when you take the thermodynamic limit, you should consider only a small subset, still infinite, but not connecting larger parts of the system. Okay, so with these expressions, you can actually work a little bit more and also determine the expectation values of the currents. You remember the currents I can define through that continuity equation I wrote you before, right? And but we don't know their exact expression here, so we don't write it. But currents, I'm just writing that currents here. Sorry, this is probably annoying. Yeah. Okay, so I was saying, yeah, currents are defined through the continuity equation of before. Where I called Qn, this is Q and J, this localized density, okay? Plus, I mean, I'm not summing to the equation, so this relation together with requiring that the trace of the current is 0. This fixes the current at least up to operators that have expectation values vanishing on any stationary state. And these currents are computed for like the most generic free system in Fagotti JPhys 2016. But we don't need their expression here, so we don't write it. It's just because you see here, I'm just fixing the difference between two currents. So if you think of the continuous formulation of it. So if I define the current only through the continuity equation, is up to a constant. So this one is fixing basically that constant operator. Yeah. Basically it's the identity times some number, and then I set that number to 0, right? If you want. Okay?
So if I take the sum of this expression over all j, it gives 0.
Oh, yes, correct. Yes, yes. But it doesn't fix a constant in J. So if I redefine J and I say that J is the one of before plus any constant plus the identity, this is getting cancelled here. So yeah, I need to fix it. All right. So now we go to, okay, this will be quite quick. So now we defined the charges, we talked a little bit about the currents, and let's briefly mention the eigenstates of this model, right? So C, eigenstates. Okay. The eigenstates of the free fermionic Hamiltonian I wrote before can be constructed by introducing a state vacuum such that C of K on the vacuum is 0 for all n. And plus noting that the commutator of the Hamiltonian with the, so I will call this creation operator and this annihilation operator, right? So with the creation operator, it's just this. Which in turns, so if you are not familiar with these relations, these are all exercises you should do. So you should prove this, and you should also prove that from this you can find now, yeah, there is another nice feature of my handwriting, which is the dagger is the same as T. But yeah, they are actually different, okay? Okay, and so using these relations, which are very easily proven, by using the diagonal form of the Hamiltonian, we basically have that these states these are eigenstates of the Hamiltonian. And the eigenvalue of the energy is actually quite simple. I'm going quite quick here because otherwise we will get stuck. Another interesting thing is you could try to write these eigenstates using the real space fermions. Okay, the result is written in the notes. It will be a later determinant. Okay. Finally, you can also consider the one-side shift operator on these states. So you define some operator T. One-side shift operator. Shift. Find some operator T that basically shifts the fermion by one side. Okay? And it's quite easy to prove that these the eigenstates are also eigenstates of this operator. Then to prove it, you basically have to use again the Fourier transform and see what the Fourier transform does, like what this operator does on the Fourier transformed fermions, and you will see that it's a very simple thing. And at the end, you find the following relation. Okay, and so basically you can find a definition for the momentum in the lattice using this operator. Okay, how is normally momentum defined? Momentum generates translations. So the lattice momentum will generate discrete translations. So basically we will write our momentum will have the property that t will be e to the I pi p, where p is the momentum. And or -1. I mean, it's just convention. And this means that these states are also eigenstates of the momentum. And I can write the eigenvalue for you in a second. We are almost done. So it's true that P on my states is equal to P K1 Kn on the state. And P K1 Kn, so this is the operator, just to distinguish. P K1 Kn is sum over J of Kj mod 2 pi. Ooh. Okay. And finally, okay, that's it. So, of course, everything I'm writing here is a very simple physical interpretation. You can interpret these states here as a collection of n particles of momenta k1, k2, kn. And you see that the energy of the state is just the sum of the energies of the single particles. And the momentum is just the sum of the momentum of the single particles, and there is actually absolutely no dependence of of interaction between these particles. So these things, k epsilon of k1 plus epsilon of k2 plus epsilon of k3, it's not affected by other particles, right? So the energy of one particle is completely independent from all the others, and this is basically another definition of the system being free. Okay. Do I have more time, or it's over? It's over in principle. Oh, I mean, I can. No, I think it's a good point to stop. So yeah, it's no problem.